Alrighty. Good morning, everybody. Can you hear me at the back? Give me a wave if you can hear me at the back. Awesome. Thank you very much. My name is Matt Woods. I'm the General Manager of Product Strategy at Amazon Web Services, and that rather bizarre title means that I get to come and talk to smart people such as yourselves about cloud computing, about the work we're doing at Amazon in building out large cloud computing platforms, and take your feedback back to the product and services teams back in Seattle, where we're going to continue to build out and add features and functionality to our platform. So this always gets left to the end. I just want to say thank you very much for the opportunity. Thank you from Mike for the invitation. And thank you all very much for your time. It's really a privilege to be able to spend 45 minutes, I have 44 minutes left on the clock, to talk to you about some of the work we're doing at AWS, some of the challenges that we face, and some of the lessons that we've learned in building out Amazon and Amazon Web Services. So as I say, I'm a general manager at Amazon, but that's my job. It doesn't tell you much more about me. So just as we're getting to know each other, I thought I'd give you an introduction. Before I joined Amazon, I worked on the tail end of the Human Genome Project, and I went ahead and sequenced my own genome. So I thought I would introduce myself via the medium of my genes. If you're not familiar, this is the device that goes ahead and sequences genomes. This is an Illumina genome analyzer. That's a username and password on the Post-it note there on the computer. Don't do that. That's not a best practice. But if you're not familiar with this device, you take your DNA and you put it on this little glass flow cell there, and you shine a laser at it, and depending on the bases in your genome, you have 3 billion pairs, 3 billion from your mother, 3 billion from your father, and depending on the bases, they fluoresce at different wavelengths, and you can read the bases on the DNA. Now, the interesting thing about this device is it moved genomics from working in sequencing genomes from decades to days, and from billions of dollars to hundreds of thousands of dollars. So anyway, I put some of my own DNA in here, and this is what it looks like. I have a propensity to be a sprinter, as you can probably tell. I have fast twitch muscles. I have a typical risk of male pattern baldness. I am genetically immune to the norovirus, which is very, very handy. I exhibit the photic sneeze reflex, which means that when I walk from a very, very dark room into a very, very light room, I will sneeze, or vice versa. If you see people sneezing when they leave the cinema, this is usually what's happening. They have the same genes as me. I have a decreased risk of type 2 diabetes, again, very handy. And this is the most fascinating. My genetic profile means that I'll drink a quarter of a cup of coffee more than the average consumer each and every day. And so that's a single base on my genome, probably from my mother, given the amount of coffee that she drinks. But if I had one from my father as well, I would drink half a cup of coffee more. So genomes are wonderful things, and now you know pretty much everything there is to know about me. The one other thing that I was going to touch on is that through my career, I have something of a habit of taking copious notes. I believe that when you're out working in science or in cloud computing or in IT generally, you can collect a lot of information and then you can learn a lot from that information. And so this is actually my current notebook. Here I am sketching out an architecture, basically whiteboarding an architecture on my notebook. And it got me to thinking that I have dozens of these things over my career. And it got me to thinking, what would the field notes look like from expeditions in the cloud? How can I help and tell a few stories about some of the work we've been doing at Amazon, some of the lessons that we've learned about building a large cloud computing platform that you guys might find interesting. So I created this field notes for you, and I'm really just going to discuss three things, three simple stories, no big deal. The first thing I'm going to talk about is how did AWS get started? How did a company, Amazon.com, that's perhaps best known for retailing? In fact, hands up, who here has an Amazon account for buying books and DVDs and awesome. Well, the good news is you're good to go on the cloud. That's all you need. So I'm going to talk a little bit about how Amazon got into the cloud computing business. I'm going to talk a little bit about some of the challenges and the lessons that we've learned from building out a large global infrastructure. And also I'm going to finally just round up with some thoughts about building databases, relational and non-relational databases in the cloud. So let's get started. So how did AWS get started? So back in 1996, this is what the Amazon.com homepage looked like. This was what we call the gateway page. You can see all the way back then, we have our old logo, Amazon.com, but it had the new name. Originally, Amazon was going to be called Cadabra, as in abracadabra, except when we tried to register the trademark, the lawyer at the other end of the phone misheard it as cadaver. which isn't really what we were aiming for. So we changed it to Amazon.com. So we got the old logo. 1996, you can see we already have 1 million titles, and we have a large catalog. And interestingly, the third item down, you can see eyes and editors. This was a very early foray that we had into using data that we were collecting on our website and using machine learning techniques to try and drive recommendations based on those preferences the customers were showing on the website. This is actually a hybrid system where we had some machine learning, and we also had human editors that would take the machine learning models and the recommendations and then use those to create personalized guidance. We don't use the people anymore, but we still do plenty of work with machine learning. So way back in 1996, this is what the website looked like. This is what the architecture looked like of the entire company. So you can see we have the internet over on the left-hand side, displayed as a cloud, even back then. And then we have www.amazon.com running the platform which we called Obidos. It's the name of the largest tributary of the Amazon. And this was the majority of the code base. And you can see that really we just have two different databases. We have one which has bibliographic information, and we have one which has customer information. Then we have some distribution centers, we have some book providers, we have customers, and we have a way to charge them money for buying things. So this is a very, very basic approach, but what's really interesting is even in 1996, this is an entirely logical architecture because all of this ran on this server. You can see the backup tapes on top of the server there. This is running in Jeff Bezos' garage, his parents' garage, actually over in Bellevue, just next to Seattle. And around the end of 1996, we started to face our first scaling challenge. And that was the point at which our bibliographic and customer databases no longer fitted on a single server. And if you've ever had to try and build a distributed system, you'll know that this is the most painful part, that when you go from one server to more than one server. Everything after that is gravy. But this is the key scaling challenge, moving from one to more than one. So we went ahead and did that. And then over the years, we went through a couple of other technical transformations. We moved into our first data center in 1998 when a water event occurred in the garage, which led us to believe that we shouldn't be operating the entire business from under a desk. So we moved into our first data center in 1998. We started to isolate out the fulfillment infrastructure in about the year 2000. So these are all our fulfillment centers and all the fulfillment operations of actually delivering a book to a customer. We moved from Unix to Linux in 2001. And by 2004, we had over 50 million lines of C++ code inside Obidos, which is the central web server, plus all the other logic that we had to run the company. That was growing by 8 million lines per quarter, and the rate was accelerating quarter on quarter. So what we had done in the race to build the business was we had gone ahead and created a big monolithic system. This had data all over the place. It was not normalized in any way. There was several different ways of, for example, doing the most simple things, such as checking the name of the customer that was currently logged into the website. That was strewn across the various different modules and components. And we had this huge monolithic system, which was just a bunch of spaghetti code. Now, monolithic systems, and you may even have some that you know of internally, they work really, really well for their intended purpose. This was obviously delivering books, it was delivering orders, it was growing the business, so it was working well for its intended purpose. However, it was becoming increasingly difficult to understand. It was very difficult for new people, new developers that were coming on board at Amazon to understand what was going on across all of this spaghetti code. And so it was becoming more and more time-consuming to adapt and modify and test the changes that we wanted to implement inside Obidos and inside the system. So increasingly, this moved from the system which was driving the business and driving the growth of the business to something which was increasingly representing a business constraint. It was getting harder and harder to modify our code base to do the sorts of things that we wanted to do. And this became more of a challenge as we started to move to different categories of items that we were selling on the website. So here's famously our second row of tabs that we added to the website as we were starting to spread out. And we have auctions and all sorts of things in there. So as we added more auctions and more categories, we had to keep modifying the monolith in order to be able to do this. It was getting harder and harder to do so as the code base was growing so quickly. We had a separate issue, a kind of parallel thread, that a lot of, as Amazon was growing in the e-commerce space, we had a lot of traditional bricks and mortar stores that were coming to us and saying, look, we understand bricks and mortar, we understand point of sale, but we want to do more in the e-commerce space, but we don't necessarily want to build that out as a core competency. And they asked us a very simple question. Can we run our e-commerce site on your platform? you guys seem to have this figured out. You've got distribution, you've got payments, it's all set up. Can we reuse your technology and your platform for our own e-commerce site? And this was the kind of catalyzing point. This is the inflection point for the end of the monolithic era inside Amazon. The monolith didn't allow us, it would have been very, very time-consuming and very costly to change it to not just serve Amazon.com and all of the logic that we had built inside it, but to take that and generalize it so that other customers could use the same platform. And it's something that we wanted to provide and we wanted to do. So around the end of the early 2000s, we had probably what was the last technical top-down decision that was made at Amazon. And that was that we were going to adopt a service-oriented architecture. We were going to deliberately move away from a monolithic system, which was growing kind of out of hand, and we were going to move into an era where we were going to build hardened APIs internally, and those APIs were going to be deliberately designed so they could be exposed to external customers eventually. So this was a key change. We were moving from an environment where we had lots of distributed data, we had a very, very complicated system, to a service-oriented architecture where we would put hardened APIs in front of our business logic. I'm sorry. So this is what the website looks like today. If you haven't read this book, I highly recommend it. The Sarlag pit there to stay on theme. But when you go to a detailed page like this, you're actually calling about 200 internal services to build out the page. So everything from the image, the name, whether it's available on Kindle, the reviews, and all the rest of it are delivered by an internal service, which is collected together and then delivered to customers on the website. So a very different model from the monolithic system. But not only did we build out a service-oriented approach to delivering our software, we also started to turn into more of a service-oriented organization. So whereas before we had large traditional development and operations teams and testings teams, we moved into a model deliberately where we had small single-threaded teams, which had everything that they needed on board to build and operate their service end to end. So no longer would development sit aside from operations. No longer would product management sit in a separate team. All of these guys would come together into a single team. They're very, very small. We call them 2 pizza teams. They're usually no bigger than you can feed with 2 pizzas. And with engineers, that's not that many. So we moved into this small, single-threaded environment where we had small focus groups that were tightly laser-focused on a single aspect of the service. So the service may be, tell me who's logged into the website. And those guys would build a hardened, wrapped API with the sort of SLAs that you need to deliver at the scale of Amazon.com, but they would be responsible for that end-to-end. What this resulted in was a huge amount of increased autonomy for these teams. They now controlled their roadmap end to end. They could add all the features that they wanted to, they could build all the things that they needed to, and they could launch quickly and when they were ready. So what we had was very autonomous small teams, kind of a big bag of startups that were operating at very, very high speed. And the polarizing effect of that across the company was we wanted to keep those teams focused on customer requirements. So we have this process which we call the working backwards process. And it starts, before we write a line of code with a new service, we start with a press release. This is a document which is written as an actual press release. It may or may not go out in that form, but it defines the service that we're going to build based on the customer benefits of that service. And then that document, and usually an FAQ that we put together at the same time, those 2 documents guide the development of the service as we go through. And it's a very handy way of continuing to refer back to what it is we were originally trying to do. So I'm not sure if you can read it up here, but this is actually the original working backwards press release for a data warehousing service. And you can see that the original goal was to do this at less than $1,000 per year. And that's the goal that we went with. So that was always one of the cost was always one of the guiding factors, and this helped us deliver that service as we went through. So this ability to be able to take customer requirements and work backwards from them is a key component of driving and polarizing these very autonomous teams without the sort of chaos that you might imagine with a whole bunch of teams that are working completely autonomously. So as was planned, we started to expose some of these APIs very, very early on as web services. Customers could pull down originally information from our catalog. So you could say, given an ISBN number, give me the author and the title and all the rest of it. Given a CD name, give me the album art for that album. And what we had was, what we saw was customers were able to take these APIs and deliver a huge amount of value to their own products. They were able to use them in inventive ways that we never thought possible and we weren't going to pursue. There was always going to be more people outside Amazon that were going to be using these APIs than there were internally. And we kind of had a blinding flash of the obvious. What would happen if we took the same approach, not just to the data that we had in our catalog, but we took the same approach to other areas of expertise which we built up over time. And one of those was building out infrastructure and building out servers and storage and all the rest of it in order to be able to deliver the sort of scale that we needed at Amazon.com. So we had this operational approach and this operational experience that we also wanted to be able to expose to customers. And that's really where Amazon Web Services came from. So this wasn't excess capacity left over from Christmas or anything like that. In fact, Amazon Web Services used up all of the excess capacity from the Amazon infrastructure in just 3 weeks of operations. So that's how we got started. We're now 9 years young. We're doing this about 9 years. I've been on board for about 5 years. And we have a very diverse range of services that we offer to customers using exactly the same approach. Now, some of these services are services which we develop specifically for customers on our cloud platform. Some are services that we build out internally, like our real-time billing and telemetry system, which we then go off and expose. Exactly the same thing we actually did with machine learning, where we took our machine learning service and then exposed that to customers. So we have infrastructure, databases, development platforms, analytics services, and enterprise services like Active Directory and all those sorts of things. And they're all delivered in exactly the same way at the end of an API with a focus and a continual drive on operational performance on the back end. So this is just a quick cartoon of what happens when you unleash this sort of thinking and ability for teams to launch quickly. And you can see that last year we added 516 major new features or services onto the platform, and that curve's going up nicely. So we're continually adding new features day in, day out, basically, onto the platform. So that's how AWS got started, but I also wanted to talk about some of the lessons that we'd learned, not just from kind of development culture and autonomous teams, but what we've done in order to be able to actually deliver this to customers at scale. So as you might imagine, AWS has a relatively large-scale global footprint. We offer infrastructure pretty much across the globe. We have 11 different global regions. I'll show you our map in a minute. And the regions, one thing I want to make clear is when customers are using cloud computing, there's kind of this idea that the cloud is an amorphous kind of mess. You lose control or visibility into your data. But one thing that we've learned is really important to customers is to respect the data locality. So customers actually have to deliberately decide where to place their data in terms of a physical location, and then we respect that. So whilst we might replicate data within that locality for durability and availability, we don't replicate it across regions because we want to maintain data locality. Sovereignty is very, very important. So over those years, we've kind of optimized our infrastructure and our network architecture to a point that I thought you might be interested in hearing a little bit more about it. So here's our map of our infrastructure. The stars are where our AWS regions are. This is where the services are physically located, and this is what customers choose from when they want to go off and deploy and start putting their applications and their data up onto the cloud. But this poses one of the kind of red alert situations that we're facing at the moment, which is all around networking. Networking suffers from really two problems. The first is that networking gear in general, the relative cost of networking gear is not following Moore's law. It's anti-Moore. So this stuff is getting more and more expensive as time goes on, relatively. The second part, which kind of compounds that and makes a perfect storm for why we're working actively in this area, is that more and more networking is being used. Particularly in what they call east-west networking. So this is networking which is used between large distributed systems or big Hadoop clusters or data warehousing clusters. There's just more data moving on the wire left and right within our data centers versus the north-south problem, which is getting the data in and out of the data centers. So we have this problem where services like Hadoop and analytics services are using more and more networking, and customers are using those services in increasing numbers, and networking is getting more and more expensive. So we realized that if we didn't start paying attention to this and start working and kind of inventing on behalf of our customers, we weren't going to have a good story to tell from a cost perspective in 3 or 5 years from now. So this is the approach that we took. Somewhat foolhardily, we went ahead and built custom network hardware, so building out the physical hardware and the routers that sit in our data centers, and putting custom protocols for the networking on top of that. And what happened is exactly what we hoped would happen. The costs of that infrastructure and that networking started to go down. We saved tens of millions of dollars on support contracts alone moving to this sort of model. But another interesting thing happened when we started to move to this approach. Because we were able to fine-tune and hone and honestly solve a more simple problem than the routers were built and configured for. If you think of the software which runs in the firmware of routers, they've built up over the years, literally hundreds of different enterprise features which live on the edges of all these sorts of functionality and features. And all we did was we stripped out all of that. We didn't need it. So we solved a simpler problem, and as a result, the number of exceptions started to decrease. So in addition to the networking costs decreasing, we started to see availability go up on the network. We were just solving a simpler problem. We didn't have to worry about all these exceptions because we own the stack end to end. So what I thought I'd do is just kind of take you through a top-down approach of how we build out our data centers and how we build out these regions. So I'm going to zoom in on our East Coast US region, which is one of our largest, and we'll start in US East 1. I'll kind of zoom in from the region level all the way down to the data centers and the servers and give you some sense of some of the lessons that we've learned in building this out and what happens when you're able to operate at a sort of scale to deliver custom networking and hardware. So this is what a region looks like behind the hood. We have what we call a series of availability zones. And a region isn't just a data center. A region is a collection of data centers which are grouped in these availability zones. And you can see here that these are connected to transit points. These are redundantly powered and redundantly connected. And the idea is that you can place your data or your applications across these availability zones and increase the fault tolerance of your application. So we have availability zones set up like this. They're typically between 2 milliseconds apart in terms of networking and latency. But in real life, they're typically less than 1 millisecond. And the reason that that's important is that it typically takes about 1 to 2 milliseconds to commit a transaction to an SSD. And so if you're doing real-time live replication and you want to be able to do that across availability zones, you need to be able to have the latency down so that you can transact across availability zones. And just to give you a sense, there's usually about 25 T peak interzone traffic moving across between these zones. So this is not an insignificant amount of networking, and that kind of reflects what I was talking about earlier. So of the availability zones, going down to the next level, we have 28 of these worldwide. Each has one or more data centers inside it, but no data center is in more than one availability zone for obvious reasons. These are fault-tolerant areas, and so the idea is that you can lose, for whatever reason, a single availability zone and your data and your application can keep running. Now, within that, we have one or more data centers, and those data centers within an AZ are less than 1/4 of a millisecond apart. So here you can basically treat them as if they are on the same physical network. And within, going down the next level, within a single data center, we have between 50 and 80,000 servers, physical servers, sitting inside those data centers. Now you might ask, well, why stop at 50? Why stop at 80? The truth is that we believe we could get to larger scale. It wouldn't be difficult to go to 100,000, 250, 500,000 servers inside a data center. However, you get decreasing economies of scale as you start to increase the number of servers. And whilst you start to increase the number of servers, you're actually increasing the surface area for any problems within that data center. So we figure that about between 50 and 80,000 servers is the sweet spot in terms of achieving the economies of scale that we want to get, and also balancing the risk of failure for the applications running inside that. We have about 102 T provisioned, and again, these are all running the custom networking and hardware that we talked about earlier. So to give you a sense of the impact of that networking, here's the old generation in the yellow bars and versus the new generation, and this is network latency. And you can see the difference here with the various different TP levels. TP 50 is the average, and then TP 100 is everything. This is also a very good lesson if you're ever doing a presentation, never to use a logarithmic scale, because it's very difficult to see even big changes. So for example, this tiny little blip here is actually a 2x average latency reduction between the old generation and the new generation. And when we go up to TP 99.9, this is the sort of area where errors that occur in any kind of frequency or variability, specifically in your application, can actually can find the bugs in your application code. So you want to reduce this variability as much as possible, and we saw a 10x latency variability improvement when we moved to this new generation of networking hardware. This is what a rack looks like. This is a large storage rack. It's got 864 disks weighing in at just over 1 ton. And this is the sort of thing that you can do when you're operating on a large global cloud computing platform. You can get really specialized with the servers that you go off and build. Not many people want to run, build, install, and manage a one-ton piece of physical hardware inside their data centers. So we're able to get really specialized in how we build these things. We're able to have very, very aggressive power utilization and storage density goals, and then build the hardware to go off and achieve those. We're also able, because we understand the thermal envelope of our data centers, to work with folks like Intel to build out custom processors. So our new generation of servers run custom Intel processors which run at higher clock speeds because we're able to, again, because we control the platform. This is compared to OEM hardware, which we can just buy off the shelves, off the rack, if you'll pardon the pun, and just install in our data centers. We don't want to do that because there's a huge amount of margin associated with that, and we want to run this as a lower cost, as close to a utility platform as we can. So building out our custom hardware allows us to reduce our costs, but also allows us to get super specialized in the approach that we take. So it's a mistake to consider cloud computing a kind of generalized, lowest common denominator platform for building out your applications. In fact, what we have at AWS is more and more specificity into the requirements for modern applications. So we're able to customize each of these different, what we call instance types, for either general purpose, but we also have compute optimized. So if you need a huge amount of CPU firepower, we have those available. We've got high memory systems, we've got GPUs up there, we've got I/O, and then we've got as low a cost as we're able to deliver. So the goal here is to provide infrastructure which is a perfect fit. Otherwise, you're trying to fit a square peg into a round hole. Here, we're trying to find as close a alignment as we can, and we're going to get more and more specific over time, because requirements change for applications day in, day out, or at least week in or month in, month out. So we want to be able to have customers have flexibility for today and in choosing the right balance for their application, but also have the flexibility for tomorrow. So a good example of this, just a couple of customer stories. The first is Novartis, a large pharmaceutical company, and they identified what they believed was a large molecule which was involved in a cancer pathway. What they wanted to do was they wanted to take their small molecular library, this is the basis for all of their pharmaceutical drugs, probably over the next 10, 20 years, and they wanted to be able to virtually screen those 10 million molecules against the large molecule which they believed was involved in the cancer pathway, with the hope that they would find an active candidate which they could use to target this large molecule and hopefully treat the cancer. So they had 10 million molecules. This is all done in silico. It's all simulations done inside a computer. And they reckoned it was going to cost, estimated about $40 million up front to go off and build the capacity to process those 10 million molecules in 39 years. So when you're treating a disease as serious as cancer, you obviously want to be able to accelerate that as quickly as possible, because 39 years is a very long time to wait for the results of a relatively straightforward experiment. It's just a combinatorial large-scale problem. Instead, they were able to run up on AWS. Instead of $40 million, we charged them a grand total of $4.2 thousand. There's a decimal point in there, although you can't really read it. So it's $4,000 instead of $40 million up front, and they completed the entire run in 9 hours. So this is a several order of magnitude change in delivering the results. And whilst all that is very interesting, the really important thing is that at the end of those 9 hours, they'd identified 3 molecules which were in the wet lab the very next day. So this is dramatically accelerating the development of cancer treatments. And the way they're able to do it so cheaply is that we have a range of different pricing options set on our platform. And one of those is that you can bid on underutilized capacity on the platform. So we want our utilization to be as high as possible, right? So you can basically name your own price for the computation that you want to run. And so you can set a price and then just spin up the capacity when it's underutilized on the platform. It's much, much cheaper to do it that way. So $4,000, 9 hours, 3 molecules found. But because of the breadth that we have available on the platform, because this isn't a commodity piece of infrastructure, we also have something as diverse as advertising retargeting. So this may seem like a way of delivering you better adverts, which you may or may not like. However, it's a super interesting technical challenge. The way that it works is a customer goes up onto a website, they go up, view the website, and then the website says, oh, here's a customer looking at me, I need to serve them an ad. And it goes off, checks the ad inventory, it goes in, sees what inventory is available, see which companies are bidding which price at that one particular time. It's a very, very dynamic market, obviously. And then generate a bid, find the best bid, and deliver the best ad to the customer. And all of that needs to be done very, very, very quickly. So AdRoll, who are real experts at this, They have about 10,000 advertisers which run on their platform, continually bidding against each other for various different customers. They're delivering this in 100 countries, and they have over a petabyte of data, 1.5 petabytes of data that they store up on the cloud to enable this. And they have a hard limit of delivering that ad retargeting in 100 milliseconds. So this is a very, very interesting technical challenge of being able to deliver that sort of environment at a global scale and do it with a hard limit of 100 milliseconds. And they're able to do that using a service we have called DynamoDB, which is a NoSQL database. And in addition to that, they also continually replicate their bidding environment across all of our different regions. So they're doing tens of thousands of writes per second across our global regions in order to keep that bidding environment up to date. Use that using Apache Storm. Under the hood, DynamoDB is delivering on the latency promises that it tries to make. So whilst I talked about the cost of our data warehouse, the benefit of DynamoDB is that irregardless of the scale that you're operating at, it will deliver single-digit millisecond latencies. And so you can see here that the average latency there, it's bubbling along. I didn't put the numbers on here, but it's bubbling along between the 3 and 4 millisecond line in terms of latency, closer to 3. But the requests are increasing significantly. And in order to deliver the sort of system that does this, you need to work and think and plan and design in a little bit of a different way. So I found this great quote, which was, "The law of large numbers are your friend until you reach large numbers." So the law of large numbers, if you're not familiar, says that the more you measure something, you get closer to the average, the more that average represents the actual performance. Now that is totally true until you get to the sort of scale that we operate at through customers like Adroll, through customers like Novartis. Maintaining that average latency, we have to do that in a very, very different way. And we actually use a system called TLA+. Any TLA+ guys in the house? No. Awesome. TLA+ is a formal definition of how DynamoDB works. It is a formal description of all of the different edge cases that DynamoDB has to deal with. And it is provably correct. So you can run your test cases, and you can prove whether DynamoDB will behave in one way or another way. It's kind of an old-fashioned computer science-y academic approach, but we use it here because it allows us to take care of that law of large numbers. And as we get to the scale, more and more exceptions can happen. So what you do is you design that formal process and that formal description, and then you test, and you test, and you test, and you test that formal description. So formal methods, if you're delivering very, very large-scale, low-latency applications, is a good lesson and something to look into. So whilst we're talking about databases, I wanted to just touch on building databases in the cloud in general. So traditional relational databases they're great. They're easy to use, they're feature-rich. Are there DBAs here today? All developers, good. Who here uses relational databases? All right, so that's about half. Okay, that's good. And you use them because they're easy to use and they're feature-rich and you can get up and running on them really, really quickly. Those are all the good sides. The bad sides are that they are very expensive to operate at the sort of scale and performance and availability that you want, and they're very hard to switch away from. You're really marrying your database provider, not dating them when you start adopting a database, particularly a large enterprise database system. And they're very administrative intensive. So you need to worry about availability and performance and scale throughout the adoption and throughout the usage of your application. As it grows and as you start to get more customers and more usage of it, those problems start to get bigger and bigger and bigger. So the admin overhead of a new database is very, very high, which means that you tend not to experiment, and it can actually slow down your rate of experimentation if the cost of failure is too high. And that's often the case with databases. So one way to do that is move away from being expensive and hard to switch, is to use more open source databases. So MySQL, Postgres, all the rest of it. However, getting comparable availability and performance to commercial databases is very, very difficult. You can do it, but the commercial enterprise databases, they're very expensive for a reason. They provide the availability and they provide the performance your application needs. These guys, it's a little harder to get up and running. And so we thought that this is another area that if we invested some time and some thought and some interest in, that we may be able to take an approach which could help out customers, where they could have the low admin overhead whilst also having low cost, but achieving the sorts of availability and performance goals that large enterprise databases are well known for. And the way that we did that, we just started with a blank piece of paper, and we started to follow our own best practices. So instead of a large monolithic database engine, we wanted to build something which was service-oriented and which was deliberately decoupled. We wanted to have something which was multi-tenant, so we could get the cost and the scale where we wanted it, and we were going to use scale-out components. We were also going to use as much of our own AWS components as we could. Some people call this eating your own dog food. At AWS, I prefer to think of it as drinking our own champagne. So we were going to use S3, our storage service. We were going to use EC2, which is our compute service. We were going to use a virtual private cloud for the networking. We were going to use DynamoDB. You might think, why are you using DynamoDB with a relational database? But it allows us to do all sorts of clever metadata work. We're going to use something called Simple Workflow, which allows us to do lots of orchestration across large, complex distributed systems. Route 53, which is a DNS service for obvious reasons. And we wanted this to be fully managed. So we wanted customers just to be able to dial up the capacity that they wanted and effectively fire and forget. We wanted to reduce the cost of experimentation for application developers as much as possible. And this is where we ended up. So this is the architecture for the product which we announced in November called Amazon Aurora. Amazon Aurora is a custom-built, cloud-native database engine which sits and runs on AWS. So first of all, it all runs inside a virtual private cloud. That means you can bring your own subnets and your own networking up onto VPC. And then effectively what we did was we started to decouple and really think carefully about where the elements of scale were inside a database. So the first part is you want a database engine. This has all the SQL and all the transactions inside it. But we started to decouple the caching and the storage. So ordinarily, these are all munged together in a big monolithic system. We want to separate those out and deliver them as multi-tenant services. So we separated out the caching, and then we put a storage layer in place which operates across availability zones. So every time you put data in, it's actually replicated synchronously across all of the availability zones. And we actually do that 6 copies across 3 availability zones. And then we routinely and continually back up all that data from the storage service back into S3. And this allowed us to get very, very high levels of performance. We're able to do 6 million inserts per minute, about 30 million selects per minute, and that's about 5 times the performance of a high-end MySQL server. It's twice as fast as trying to do it in RAM. So this is a very, very high-performance system which has everything you need for highly available systems because we have this 6-way replication across 3 AZs. That means that it's designed to deliver 11 nines of data durability. Very, very durable system. Additionally, it's much more fault tolerant because we separated out the caching. So that means that you don't have to reheat your caches if your database engine crashes for any reason. You can just start it up, then the caches are already there, and you don't have to reheat, and you don't get the performance hit of having to restart. And crash recovery takes seconds, not minutes. It's much, much faster because we're able to immediately restore the state into the database engine because we separated it all out. So that's one approach of what you can do if you have decoupled autonomous teams working with very, very flexible infrastructure and being able to deliver the sort of invention that customers need in order to meet performance and availability goals for their databases. So that's pretty much all I had, just 3 simple stories. We talked about how AWS got started, we talked about building out a cloud platform, and we talked a little bit about building databases in the cloud. I think the key here, the key takeaway when I was putting this presentation together was that when you couple developer autonomy and you couple that with flexible infrastructure, which is built on and maintains an operational and security focus, there's really never been a better time to build. And so that's what I hope for all of you, to be able to build wonderful applications which your customers will love. And with that, I'd like to thank you very much. Thanks a lot.